Okay, is my volume okay? Can you hear me? Wonderful. So thank you, Jean, for the introduction. My name is Emily Cunningham, and I'm just finishing my third year here at UC Santa Cruz. And I'm very excited to talk to you today about work that I've been doing with Alice Deason, Raja Guhatakirta, and Connie Rakasi here in Santa Cruz. But I also want to take a moment to acknowledge my collaborators, Evan Kirby, Roland Vandermeerel, Jay Anderson, and Tony Sohn, without whom this work would not be possible. So I want to take us back to yesterday. At the end of the discussion, we were talking a lot about how we'd really like to understand the Milky Way's mass assembly history, and how this is very difficult, in part because we see in simulations that halos that end up with a given mass can have a wide variety of assembly histories, and our constraints on the Milky Way's assembly histories are very limited. And I hope to convince you that there's a glimmer of hope in this problem, and this glimmer of hope is in the stellar halo. So studying stellar halos is extremely helpful in understanding assembly histories because the stars trace the dark matter. So here I'm showing you 6 different halos. These are the Cooper Halos Aquarius simulations. And what you can tell right away is that these halos look dramatically different. And this is simply a result of their varying accretion histories. So simply mapping out stellar halos can contain valuable information about the accretion histories. But even better than the positions of stars in the halo are their kinematics. Because the orbital timescales of halo stars are so long relative to the age of the galaxy, the kinematics of halo stars contain a strong link to their initial conditions. So by studying the kinematic structure of the stellar halo, we can start to try and disentangle the Milky Way's formation history. However, this has been pretty difficult, and as we saw yesterday, there currently aren't very many observational constraints in the stellar halo beyond, say, 10 kiloparsecs. SDSS really blew everything up locally and discovered a wealth of substructure in the stellar halo, but from a kinematics perspective, beyond 10 kiloparsecs, we're limited first to only velocities in one component, which is along the line of sight, and second, we're limited to only the line of sight velocities of rare tracer populations. We have very limited kinematic information beyond 10 kiloparsecs in our own halo. So this is where we come in with HALO7D. So HALO7D is a spectroscopic survey using KEK2 and DEIMOS of distant Milky Way main sequence turn-off halo stars that have measured HST proper motions. So these HST proper motions have come up in a few talks in this conference, and I just want to emphasize what a game changer these measurements have been for local group dynamics. They've really blown open what we're able to do in the local group in terms of studying kinematics. So these measurements are really heroic and have only been done for the first time in 2013. And so because we're targeting a very deep distance range, we're trying to get to 10 to 100 even kiloparsecs, we have to stare at these stars for a very long time. So we integrate on each mask for a minimum of 8 hours and up to 24 hours. We've been very grateful for the support of the UC-HiPACC, and we've been awarded an outstanding 25 nights in my 3 years at graduate school on KEK to do this program. So this program is going to give us 3D kinematic information, so 6D phase space information for approximately 350 halo stars. I also want to note that this data set will be unique even in the era of Gaia, whose limiting magnitude is approximately 20, whereas we are going down to 24.5. So Gaia will blow up the inner halo and provide amazing statistics in the inner regions of the halo, but we are really going for depth in this program. So I told you it's HALO7D, so the 7th dimension is metallicity. So we are going to measure iron abundances for our stars that are brighter than 22.5, and also alpha abundances for stars that are brighter than 21.5. And this additional information will be huge in trying to understand the Milky Way's evolutionary history. This is a survey that is taking place in the candles fields, and that is because candles are characterized by many deep multi-epoch HST pointings that are contiguous, so we can observe multiple HST pointings with a given DEIMOS mask. And we also have an exciting opportunity here for extragalactic studies because there are only, say, 25 halo stars on a given DEIMOS mask, which lets us fill the rest of the mask, another 100 objects, with distant galaxies, which can take advantage of our deep integrations. So I encourage you to speak to many of the people in this room, in particular David Koo, Sandy Faber, Hassan Youssef, and Yicheng Guo, about their programs that are filler targets for HALO7D. So there's a lot that we're going to be able to do with this data set, but I want to start by by just explaining our first result from this survey that came out earlier this year in order to demonstrate the kinds of things we might learn from HALO7D. So our first result are 3D kinematics for 13 Milky Way halo stars that are along the line of sight of M31. Now I know there are only 13 stars, but these are the first 13 stars outside of the solar neighborhood for which we have 3D kinematics. So this is a quick summary of our kinematic sample where we have proper motion in galactic latitude on the y-axis and galactic longitude on the x-axis, and these points are color-coded by line of sight velocity. And the first thing you might notice is that it doesn't look like there's particular clumpiness or structure in our sample. Our sample is not dominated by one cold stream, say. It looks like we're looking at halo stars that have a distribution of kinematic properties. We see this again when we look just at the line of sight velocity histogram. So this is a cumulative histogram. And I'm showing here that the best fit dispersion, which is about 91 kilometers per second for our sample. And in contrast, Triand, which is known substructure along the line of sight between us and M31, is shown here in red. So we're clearly not dominated by a cold stream in our sample of 13 stars. So what we decided to do with our 13 stars is provide an estimate of the velocity anisotropy. So for those of you who don't spend all day thinking about velocity anisotropy, I'll just remind you that beta is given by 1 minus the total tangential velocity dispersion in the numerator divided by the total radial velocity dispersion in the denominator. And so what this means is that if we have a value of beta equal to 1, we have a population of stars that are in perfectly radial orbits. And beta equals negative infinity corresponds to a population of stars on perfectly circular orbits. And so here I'm summarizing all the information that's known about the velocity anisotropy in the Milky Way as a function of radius. So I have beta on the y-axis, where again 1 is radially biased and negative infinity is tangentially biased. And I have galactocentric radius on the x-axis. And my point here from these 13 stars is shown in pink. And we find approximate isotropy in our sample. Up here is the solar neighborhood point. The solar neighborhood point finds radially biased anisotropy. And it's quite unexpected that we would see this decrease as a function of radius. We expect as we go farther out in the halo that our stars overall would be on more radial orbits. We also see this sort of decrease in beta in other observational studies. But I do want to point out that all of these points here were measured using only line of sight velocity distributions. Our point here and the point in red are the only 2 points on this plot that use 3D kinematic information. And when you use only line of sight velocity distributions, you have to make assumptions about the Milky Way potential. But this decrease is unexpected. And it also is sort of curious that this decrease is appearing right around where we observe a break in the Milky Way's stellar density profile. So what we want to do is explain these two pieces of evidence in tandem. And we suggest that this could be evidence for a shell. And by a shell, I mean a relic of a relatively massive early, or maybe several early synchronous accretion events that would both cause an increase in tangential motion relative to radial motion, as we observe in the decrease in anisotropy, and could explain the steep drop-off in stellar density beyond this radius. However, that's not the only explanation, and I've made this argument to you based only on 13 stars. And so what I hope you can appreciate is that with HALO7D, we will have hundreds of stars in which we could investigate the structure of the stellar halo. We'll have 4 new lines of sight along which we can measure beta. We can recreate that plot I showed you for beta as a function of radius exclusively using points that have measured 3D kinematics. We're also going to measure chemical abundances, which will greatly help to characterize this shell if we continue to see the shell as we increase our statistics. And the chemical abundances will be great to try and estimate the mass spectrum, say, of accreted dwarfs in the Milky Way's halo. In addition, Gaia is going to be fantastic for improving our statistics in the inner halo and providing extremely precise proper motions, though at the distances we are probing, they will only be giving us proper motions for the rare tracer populations. So I will leave my conclusions up here. Thank you very much.
Question for Emily? A comment and a question. I mean, this is really cool that one is able to do this. So the comment is that the break in the profile, which in HST photometry looks actually really clumped up, and it looks as if it's clumped at distances around that, but the distance varies from field to field. It's actually pretty interesting. But it's along all the HST survey fields, and it's along all Sloan sight lines. So this is not just an M31 phenomenon. It would be everywhere.
Absolutely, and that's why we want to look in the velocities to see if we see some sort of evidence of global substructure.
But then when you showed the proper motions, they weren't. They were offset from zero on average.
Yes.
Is that just because of solar motion?
Exactly.
Okay.
That is absolutely correct.
I just wanted
to make sure.
Clear because it's
yes. No. All the points are clustered offset due to the solar motion.
Okay. And whose solar motion did you use? Because I know there's a fight about it.
Yeah, I want to say.
Does it matter?
That's a good question. I doubt it matters, and that's a good thing that's worth investigating given that there is a fight about it. I want to say we used Schonrich 2010. Yeah.
Any other questions for Emily? Okay, thank you. So,